It's just amazing to try. Okay. I'm like nothing. Okay. So we do that. Yeah.
I have a friend that you know. Okay.
My boss started working for Northwest. He was living for a lot of time. He was always long. You know, it's just fun to go back to that. All right.
Mixed in. Hey, is that one? Because it was hard to get pictures in.
Not that bad.
I know.
I'm not sure. No. And that's good. Yeah. See, I was. We could afford to. When we first got here,
You don't want to be living
Yes.
Hey, what's up?
How's Noah doing?
He's good.
Yeah. Practicing law or doing something else?
Yeah, he's been working for these employment lawyers, this firm that's over by Project. He does contract work. As he can put it in.
Okay.
So it's been nice. It's been something to do.
but not
Yeah.
full time. And
Yeah, I mean, we still need a lot of flexibility. Like Henry's at school right now because when they do the flu mist at school, he has to be gone for a week because he can't be around the live virus.
Gotcha.
So this is the second time they've done the flu mist this 9 weeks. So he's like out.
Today. Do you have how'd you like that? We're going to send around a little evaluation survey monkey thing. And so what we're going to do, we've had some folks ask about what we're going to do with the all the work that we did yesterday and what we'll do today. We'll have hopefully out on Friday the list of needs that we came up with yesterday afternoon. Of course, all the presentations will be put on the website so that you can see them. Jim, is this one going to be recorded too?
Yep.
And so through Jim's work, we'll have the video up, and so. Today, we're going to have at the end of the day, remember yesterday we did the thing with what are the needs, and then today we're going to come up with another list of what are solutions and that can, or suggestions to address those needs from what you've heard. So please take notes, and as speakers talk and show you what they're doing in these case studies of the international case study and also the water management districts and all, and also from cities, such as the city of Tampa is going to be presenting. Then we want to take a look and see what is there. And that's one of the things that we talk about in every single group of the needs. What was the number one thing you think was cleared in every single group? Why, it obviously was, we need to find out what's there before we invent something else. And so Florida Earth is all about reinvent the wheel. Let's work together to figure out how we can combine knowledge instead of spending millions of dollars to do something that somebody else has already done. So, get there? Get. Okay. Who's new? So just shout who you are. So everybody knows you.
Okay, hi, I'm Susie Kaufman. I'm with Jones Edmonds, a consulting firm in town.
Okay, and Roberta?
Hey, good morning, everybody. Excuse me, my name is Roberta Starks. I'm the data collection bureau chief at this office for mortgage.
Al?
My name is Al Carter. Good morning. I'm the Southwest Florida Women District. I'm trying to try to replicate
But notice he said try to collect big data. Yeah. Who else? Carl.
Good morning, Carl Craig, City of Tampa, Technology and Innovation. I try to provide the utility departments in the City of Tampa the technology resources they need to conduct business, which would include data services, needing more big data.
Okay. If you will, during the day, I really don't need to take these brochures back with me. So everybody get some of the stuff we've got on the table here. This is the commercial part of advertisement. May the 9th to 13th is our U.S. Netherlands Connections next delegation that will be taking over. If you want to become a part of that, please take a look on the website. And the very first class that we did in 2007 is represented here. Matt Hale went on that class. And how many have done the trip? Peter and Tom and Matt Hale. So they can talk to them about it, and you'll find that it is something that is an experience of a lifetime. And then at lunch, we'll talk a little bit more about some very unique things that we're doing. So are we ready to go? Okay, our first speaker is Steve Bourne. Steve works for Atkins, which is a global consultancy headquartered out of London. And you might have seen Atkins from the work they did. If you haven't seen anything else, that they did the London Olympics was one of their big projects. So engineer of record. Yeah. Engineer of record for the London Olympics that built the village and the whole works there. So why don't you just tell a little bit more about yourself and some of the things that you do, and this is a really cool presentation.
Given Stan hasn't actually seen the presentation, I hope that's true. I'm Steve Bourne. I'm from Atkins, as Stan said. I'm a project director in our North America office, and I am the R&D chair of the North American office. My background's actually in water resources engineering. I am not a gator, but I am a yellow jacket, so I feel a certain kinship through our rivalry with Georgia. University of Georgia, right?
Yeah.
We love you guys. Anyway, the work that I do, like the background is in water resources engineering, but I actually do software development a lot of the time. Mostly developing software for water resources engineers, and now branching out into lots of other areas in civil engineering. So, making data fun was not the title of my talk. I think Stan assigned me that title. So I'm hoping that by virtue of the fact that we're talking about big data, it's going to be fun. But I also added and valuable, because that's really what the focus is. Part of my first interaction with Stan was to come up with an idea for an app. Stan didn't actually ask me to do that, I just did it anyway because I developed iOS apps. The idea was, let's make an app where you can go to the ocean and stand at the water's edge and make a record of that's where the water is. Why would we do that? Well, firstly, it's so that I can take my wife on dates. That's her feet, by the way. But the larger picture is that we would get a record of sea level rise. Like, imagine if everyone was doing that for the last 30 years. We would get a pretty good picture of sea level rise. And what's interesting about this app idea is that it really brings out all the issues of big data. Big data is kind of anathema to us in the science field, because as someone was saying yesterday, we're focused on systems and understanding the mechanics of things. And big data is really about just record everything that you see and figure it out later. So, this app in and of itself brings out that idea. If you're a cartographer, if you're a hydraulicien, if you're a fluid mechanics person, if you're a CFD modeler, all the fields that you can think of, you have real problems with this app. Because, think about it. Think about if you're a cartographer, you have to think about which datum are you using. You're making a record of where the sea level is. Well, what datum? What is zero? If you're thinking about fluid mechanics, what tide level are you at? you know, if you're thinking about kind of any field that you think about, this is going to cause big problems. You know, how do you work out this data? This data would be incredibly noisy if we actually recorded it. But in the world of big data, you record it anyway. And so that's kind of the start of this talk. I'd like to thank Stan for inviting me to do this, because it let me do some research on big data and understand what big data is about. Someone mentioned yesterday the V's of big data. There's actually, it started out with 3 from a guy named Doug Laney at Gartner back in 2001. And he defined volume, velocity, variety. That's what big data is about. Those are the dimensions that you have to worry about. And lately, they've added veracity to it. Is the data that you're recording true? How true is it? How precise is it? How accurate is it? Volume, like I said, don't sample, just observe. So, you know, the idea is that, you know, if something is happening, record it. That's the big data idea. Velocity, the spigot problem is what it's called. You know, there is a massive stream of data occurring at all times, and you are going to run into problems if you think about, you know, actually recording that and storing it. Variety, text, images, video, audio, all of that. All of it is big data. All of it needs to be recorded. When you get into video, I mean, think about the volumes. You know, what does YouTube have to deal with? It's a massive amount of data that you're talking about. And then, you know, veracity, question the truth. Is what you're recording actually true? Is it a measure of what you're trying to record? So I went further into big data. I wanted to find out, you know, what are we talking about here? This is a diagram of what we call prefix multipliers. Prefix, so you put kilo, mega, giga, tera, peta, exa, zeta, yada, that was a new one for me, in front of byte. And that's when we start talking about, you know, the size of data. Kilo is 2 to the power of 10. Mega is 2 to the power of 20. They roughly match up with 1,000, a million, a billion, a trillion, and so on. But that is really the measure of data. Where is big data? I don't know if anyone calls it small data, but that's what I'm doing. Basically, out to about the giga level, that's the stuff you can keep on your own PC. That's the stuff you can work with on your PC. Past that is what we call big data. You can't actually feasibly work on a big data set on a single PC. It would take you too long to process it. It's the kind of thing where, you know, it takes you 1.5 years to process 1 year of data. You know, if you do that, you'll waste your whole career. You'll never actually get to an answer. And so you need to parallelize. You need to bring in lots of cores, lots of computing power to work with big data. Here are some examples. These are fascinating. I wish I could do more of these. Your standard smartphone is about 32 gigabytes, 64 gigabytes, so you can see where that lands on this scale. The next one is 3 petabytes. That's the Library of Congress. The next one is 32 petabytes. That's the storage in NASA's Center for Climate Simulation. If you keep going, you get to the Hadron Collider, 200 petabytes. That's the annual storage from the Large Hadron Collider. So everything that they are sensing in the collider makes up about 200 petabytes per year. What's interesting is that's about 1/1000th of 1% of what is actually being sensed in the Hadron Collider. They have to, that's the spigot problem. They have to kind of ignore a lot of it. Go out further, you get to Facebook. So Facebook has more storage than the Large Hadron Collider. 300 petabytes, that's Facebook's data warehouse. And then if you keep going, and this is what I found most fascinating, 67 exabytes is the amount of data that's actually transmitted in the world every year. So imagine how many libraries of Congress are transmitted every year across the world. Here's an example of the veracity problem. How big is the Library of Congress? There are blogs and blogs and pages about whether you can use the Library of Congress as a unit of measure of big data. And the brackets that I have up there give the range of how big the Library of Congress is according to different people. So the lower end there, it's about 15 terabytes. The higher end, 3 petabytes. And it just depends on which part of the libraries you're including. Like there are digital stacks in libraries. If you include those, you get to the petabyte level. If you just include the text, it's the terabyte level. So no one really knows how big the Library of Congress is. And so, a lot of people try to use it as a unit of measure of big data. The truth is you can't really do that. So what about environmental science? What's big data and environmental science? Did more research on this and included some of the sources that I've been using throughout my career. There is a real-time deforestation watch. That's the World Resources Institute is doing that. So in real time, they're tracking how much deforestation is occurring across the globe. Citizen science, this is from Oxford University. That is a network. It's not really a single study, it's a network for people to actually add algorithms to work on big data. Encyclopedia of Life, this is a database that has a record of every single species known to man. I think there are about 2 million of them. And there's pages, there's observations of those species, there's history of those species, all of that. GCMs and downscale models, I'll get into that a little bit later. I think we talked about that yesterday. Those are big data. That's the whole globe being modeled on an hourly time step for centuries, 500 years, that kind of thing. Quasi is the, let me see if I can get this, Consortium of Universities for the Advancement of, oh, I spelled it wrong, for the Advancement of Hydrologic Sciences Incorporated. That is an agency that's been around for, I guess, about 10 years now, and their mission is to store water data. And they have done a really good job creating standards, creating a network, federated network of servers that have water data around the world. Lots of good stuff there. The federal government is big into collecting data, National Elevation Data Set, National Hydrography Data Set. These are all data sets that have been created over the last 10 years and are getting more and more detailed and bigger and bigger. And then something that myself and Jack Hampson, who's in the audience from Atkins, is working on is the Open Water Data Initiative and the National Flood Interoperability Experiment. These are efforts going on right now to make data more open and open to scientists and make it possible for scientists to essentially donate their analytical capabilities to the big data problem. Given all of that, it sounded like it was a lot of data, but compared to Facebook, compared to Google, compared to those efforts that are more in the commercial space, data still, big data and environmental science still has a long way to go. This was a very short but kind of sweet quote that I found, that trees can't tweet. It's true, people can, and so the big data sets in the commercial world are getting bigger and bigger. Trees can't do that, and so we have to put in a lot of effort to actually make big data happen in environmental science. We also need people. This is kind of an infamous quote from, this guy was the chief data scientist at Facebook. The best minds of my generation are thinking about how to make people click ads. That sucks. The millennials, you can't accuse them of being indirect. That really does suck. And I think that conferences like this are important to bring people out of that world and into the world of science. Okay, so what's the challenge? We've been talking about big data at this conference. We've been talking about big data for decades now, actually. What we have found is, this is called the value tree, data, information, knowledge, wisdom. What we have found, the challenge is that using data to build knowledge, that's really the way to go. In big data, the kind of mindset is just record everything. But in our science world, we found that we have to really think about what wisdom do we want to gain, what knowledge do we want to gain before we decide which data to collect. So actually the rest of this presentation is kind of about that. What applications have we been building at Atkins that think about that knowledge, think about those decisions we want to make, and which data have we collected to do it. Okay, so I think I have 4 examples of where we've used big data. Each one starts out with a page like this. So there's a little background section, there's a decision that needs to be made. These are decision support systems, so we focus a lot on which decision actually needs to be made with them. The stakeholders that are involved, the key engineering questions, and the key natural systems questions. North Slope Decision Support System was a project that we started in 2008. It was sponsored by the Department of Energy, U.S. Department of Energy. It was the partners that worked on it were University of Alaska Fairbanks, ourselves, and Texas A&M University. The key decision is where should we build an ice road? On the North Slope of Alaska, it's an oil-rich environment, and oil companies want to explore. Basically, they do a lot of geotechnical work to figure out where they think oil is, and then they have to go out and actually drill for it and try to find it. The problem is that up there it's a tundra environment, so it's environmentally sensitive. Also, there are endangered species up there. There are tribes up there with culturally important lands. So, it becomes a clash of stakeholders to do this oil exploration process. The only acceptable way to get across the tundra is to wait till winter and build an ice road. And so this tool was built for the stakeholders of that process to figure out where the best places to put ice roads are. It's not an analysis that a single person can do. It actually has to be a consensus among these stakeholders. And so this tool was built to bring transparency to that process. Key engineering questions, how much does the road cost? That's what the oil firms are interested in. How long do we have to build it? Does it avoid sensitive environmental areas? Does it avoid cultural resources? The key natural systems questions are impact on Arctic lakes under climate change. The material to actually build the road is from lakes on the North Slope. Under climate change, what they found is that the season to actually use the water from those lakes, when it's cold enough, has gone from 200 days per year to 100 days per year in the last 30 years. And so, understanding where are the lakes, how much water do they have, what species are in them that we might affect, how long are we going to have to actually pull that water from the lake and build the road, all important questions that this tool tried to address. In terms of big data, the NSDSS was a North Slope Decision Support System. It was really a variety issue. We needed a lot of different data sets: topography, transportation, endangered species, tribal lands, lake bathymetry, species within the lake, meteorology, general circulation models, regulatory buffers. That's just a few of them. We had to bring all that together to actually answer this question. The folks from Texas A&M, we told them, all right, come up with the best way to actually find the ideal ice road route. They came up with ant colony optimization to do that. Apparently, ants are very good at finding the most efficient route under lots of different constraints. And so the tool actually employs ant colony optimization with all those different data sets I talked about to find the ideal route. Avoiding polar bear dens, avoiding the environmentally sensitive areas, keeping the cost minimized, keeping the safety maximized. This was the routine that we used to do that. Another interesting thing we did with the data was suggestive lake climate change impact modeling. The challenge is kind of our mission statement: automatically create a water budget model and a dissolved oxygen model for any lake on the landscape with a climate change forecast involved. So there's 15,000 lakes in our database covering the North Slope. We wanted to be able to click on any of those lakes and automatically create a water budget model for it and a DO model for it. And we actually created a routine that does this. We introduced a module called the semantic modeler. So we were kind of thinking bigger in terms of what type of model you can use. A semantic modeler actually can implement lots of different models, sort of interprets what you mean by a model, and pulls the data to actually create the model automatically. We had a really good process here for working with the universities. We actually, we're not the modelers at Atkins. The universities are coming up with a way to do water budget modeling in the Arctic. And so we said, just write that down in a white paper and we will code it. And it turned out to be a really good way to do it. Rather than ask the researchers to write the code, they would just describe what model they wanted and we would write the code and put it into our semantic modeler. The modeler pulls from data sets, from big data sets, GCM-based projections for the climate forecast. From the university's meteorological data set, we pull historic weather. And because it's a semantic modeler, it actually ties into lots of different databases and can pull data in a suggestive process for modeling. Making polar bears fuzzy, this was another issue. This is actually an interesting issue in terms of big data, because what we were doing was increasing the, increasing the veracity. We were decreasing the veracity on purpose. There are databases from an organization called GBIF from Encyclopedia of Life that has precise observations of polar bears. So if you actually use that data set, you can go out to the North Slope and get a pretty good chance of actually running into a polar bear. What we decided was we don't actually want to put that online as information because there's pictures of polar bears. And so what we actually had to do was introduce something called a fuzzer, which converts the data from precise observations to probabilities and coarsens it accordingly. So there you have an issue of actually decreasing the veracity of the data. You have much more precise observations than you want to let out there. That was an interesting process. Okay, the next presentation is about Stormcaster. Stormcaster came out of the North Slope Decision Support System. In that process, we actually built a server of GCM data. GCM data is big data. And actually getting that data for a particular part of the world is difficult. It was difficult at the time. This was 2008. The data that comes out of GCMs is in a binary format. It's difficult to read. And so we created a service, essentially, that any tool can tap into and say, I want a GCM projection for this part of the world, and it just feeds it out as standard ASCII data. So what we built from it was a tool called Stormcaster. And what this is an online tool that anyone can access at AtkinsStormcaster.com. And you can go to your town and kind of pick a historic rain gauge there, and it will give you a forecast of how your 100-year storm is going to change over the next 100 years. What we found, actually, when we looked at some research from NOAA, was that the assumption that we often use that 100-year storm, a storm that will occur with 1% probability, the assumption that we take is that that's staying the same through time. It's stationary. Stationarity is dead, and this is a perfect example of it. It's actually changing over time. What we can see in these two charts here is the last 50 years, or at the time, the last 50 years, 1958 to 2008. This was published by NOAA. And the map on the left shows the percentage change in annual rainfall across the United States. So the southeast is getting drier. The northeast is getting wetter. This is not projections. This is not models. This isn't UN IPCC. This is actually recorded historic data. And so you can see that, the 100-year storm, that assumption is wrong. It is changing. And, the chart on the left actually goes to the extreme events and shows the increases in the amounts of very heavy precipitation over that same time period. You can see in the northeast, that's actually increased. Essentially, the 100-year storm has increased by 67% over the last 50 years. And so what we wanted was a tool that looked at how is the 100-year storm going to change as we move into the future using the GCM projections. And so this is a single slide that describes the algorithm that was developed. I'm not really going to go into too much detail on what the algorithm is. That requires a longer presentation. But essentially, the tool in the end allows you to pick any city in the United States and produce this forecast. The example that you see on the right there is for Atlanta, and what it shows is that Atlanta precipitation for the 100-year storm is going to increase about 20% by 2050. And so if you're FEMA, if you're GEMA, Georgia Emergency Management Agency, if you're Atlanta, if you're the other cities around Atlanta, you need to be worried about that because the floodplains are changing and increasing accordingly. One of the topics we talked about yesterday was, okay, we're sharing a lot of data. How do we share analysis? How do we make it possible for people to provide their analytical brain power to others? How do we share that? One of the things that we're doing with Stormcaster is we're creating the Stormcaster network. The algorithm that we developed for downscaling GCMs and making that forecast, it works in some places, it doesn't work in others. You know, in the desert Southwest, for instance, that algorithm is not going to work that well. And so we're creating an ability to actually submit your algorithm for creating a forecast that will use the big data and produce the result for you. Here's another example, transportation planning in the UK. We at Atkins were kind of the engineer of record for the M25, which is the loop that goes around London, the freeway. And one of our charges for that is to come up with, in transportation modeling, you come up with a trip matrix, is what it's called. And this basically just defines all the different destinations that you can go to, and defines how often trips are made from one destination to another. Traditionally, what we've done with that is we do surveys. Basically, you stop people on the side of the road and ask them where they're going. You know, that causes lots of problems. Chief among them is that you are increasing congestion in the highway that you're trying to decrease congestion for. But you're also introducing a lot of bias in that process. And so recently, we made a partnership with one of the larger cell phone companies, does about 40% of the cell phones in the United Kingdom. And we are using their data, what they call breadcrumb data, which is, you know, every time you use your cell phone, you know, pull up a map, or anytime you're sharing location information, that information is going somewhere. And in the US, it's going to Google most of the time. And you can use that information to figure out, you know, where people are traveling. And so we have introduced a lot of new algorithms that use this spigot of big cell phone data to do our travel matrices. The issues that pop up with that exercise are velocity and privacy. You know, the big issue, it was interesting, I was talking to people from the UK about this, and they said, you know, the thing that we're worried about is The Guardian, the newspaper in the UK. We're not worried about being sued. You know, we don't care really, I mean, they care about it, but it's definitely a lower priority. We are worried about press, bad press for using that data. And so, you know, people are worried about, you know, how do you, basically Big Brother keeping track of where they are. And so there are a lot of measures in place that anonymize that data, that aggregate it, that bring it to a point where you really can't track it down to the individual. And that's a big issue in big data. And then of course there's the velocity problem, the spigot problem of 1.2 billion events per month. That's with 4G. When we go to 5G and start introducing Internet of Things, where the cell phones are actually communicating with, you know, your coffee maker, to tell it to make coffee because I'm coming home, that data is going to explode. And actually bringing all that data into, you know, we have a tap essentially of all of that data. We have to record it, aggregate it, throw it away a lot. There are big algorithms in place to do that. Another example is growth forecasting. This is for Atlanta. We have a population forecasting tool that essentially, it'll take a regional projection from an econometric model, and it'll disaggregate it down to what's called the TANS level, traffic analysis zone level. So it's taking, you know, Atlanta's going to go from 6 million people to 10 million people over the next 40 years. It's taking that data and saying exactly where those people will be over time. You know, allocating new houses, new commercial buildings, new parcels. There are 22 million acres in the Atlanta regional area, and it's modeling every single acre over time. How does it do that? How does it know where things are going to be built? This is called a likelihood raster that it uses. It essentially uses expressways, major roads, commercial land uses, other factors that are geographically based to produce a likelihood of development over time. And it allocates new growth to according to this likelihood raster. I have an animation here. I hope it's working. This is the result of the model. You can see Atlanta growing. I think this one goes out to 2020. Yellow is residential, and red is commercial. And so, you know, this is definitely a big data issue. We're working lots of data to make this happen. Okay, so those were examples of things we've done in the past, and now I'm going to get into what we're doing now. Silos are dead, especially analysis ones. This is a statement that has a veracity problem. It's not true. Silos are still very much alive in terms of data, in terms of analysis. We, in our industry, we are transportation engineers, water resources engineers, planners, population projection scientists. You know, we're in silos. The data that we have is in silos. The analysis that we do is in silos. And so silos are dead is an untrue statement. But we are going in a direction where we're trying to make that true. We're trying to join all that together. And the way that we're doing that is a new initiative we're calling Future-Proofing Cities. It's been around for a little while now. We first focused on the developing world, India, places in the Far East. And what its focus is on building resiliency in cities. I'm actually the North American leader of Future-Proofing Cities for Athens. And we are crafting for the developed world a method for understanding resiliency in cities and for building resiliency. The process is it's very stakeholder oriented. Essentially, you start on the left with your stakeholders and your team of experts, and you develop master plans for your city, scenarios of how you'd like to build resiliency in your cities. And then in the center there, that's where all the Athens experts come together and our partners, and we do something called stress testing, where we take your master plans, which traditionally master plans are a city planning exercise. They're kind of aspirational. The city doesn't actually know that they can create the city that they're coming up with their plan. It's sort of like what we'd like to do. We're introducing the stress testing process that models the population growth within the city, models climate change as it's occurring and affecting the city, models sea level rise as it's occurring and affecting the city, and other disasters as well. And we are evaluating whether these master plans will actually work or not, in a very quantitative, very realistic way. We do that for an extended period, basically working with external drivers to the city, simulation model that we're developing right now, and measuring the city in terms of how well it's doing under the master plan. And then we take all of that back to the stakeholders, and we build a consensus on which master plan they actually want to go with. So, it's a very sort of a next generation of master planning process that we're developing right now. Community stress testing, this is kind of how it works. The bad community is the red line, the good community is the green line. Or put it another way, the less resilient community is the red line, the more resilient community is the green line. And we are literally modeling the city over this time span. We're going from 2015 to 2050, actually. And we are modeling business as usual in the city as the population grows, as the economy grows, and we're also modeling disasters as they hit the city. One of our first examples that we're working on is the Dominican Republic, different cities in the Dominican Republic under a USAID grant. And you know, the disaster of concern there is a tropical storm, it's quite like Florida. And so, you know, this simulation model is actually modeling those storms as they hit the city and destroy houses and buildings, and how the recovery of that occurs on a building by building basis to evaluate the resiliency of the city. We do that for a base case, like the current infrastructure for the city. And then we do it with the master plan, where they've introduced things like seawalls and other measures to counteract climate change. And we evaluate how effective those are going to be. Stress testing, so I mean, this is another illustration of the process. You know, you have multiple master plans, they all go into the stress test. And at the far end, you get a result, which compares the different master plans and calculates with those box plots the uncertainty in the analysis that we're doing. Okay, that's it. But one other thing, we actually have a display over there that has some of the future-proofing cities products that we've been producing. There's a report card that we do for a city at the beginning of the process that looks at, you know, how well the city is growing, what the economy is like, how vulnerable it is to climate change and sea level rise. There's some products over there that you're welcome to take. Okay, that's it for me. Any questions?
We've got some time for questions for Steve. I'm gonna just ask him a question on. There are quite a few, not quite a few. I think we're going to be one of the first ones with a citizens sea level rise type application with the Seymour app. Can you, how much? If one person standing on the water and pushing the button and recording where sea level is, that second is nonsense. You kind of understand that. But 1 million people doing it, then all of a sudden you get some things that you can work with. I know that you developed this for Apple, or we're working with the Apple process. Would it be hard to get it on Android and the other?
No, not at all.
Okay.
Yeah, there are ways to you develop it once actually, and it ports it out to the different platforms.
Okay.
Yeah.
All right. This is. Are there many of those around?
Not that I know of.
Yeah, I think this.
We do that research every time we come up with an app idea. You go to the App Store and make sure no one's done it. And I didn't see anything like that.
Yeah, I think we're one of the first ones to have.
Steve, the NOAA study that shows rainfall is on a decreasing trend in South Florida. Be very careful about using that. The reason is the GCM, general circulation model, the grid size is very big, 50 kilometer by 50 kilometer. There's a very active area of research on trying to downscale those models to localize weather pattern. And what we have seen in South Florida is very hard to look at those GCM results and just stick to them. It's that veracity, the part that you brought up, it's very critical. So there's people that are doing this research trying to downscale this model. One example is sea breeze has a major impact on rainfall pattern on the coast. And some of those sea breeze dynamics cannot be captured in a 50 kilometer by 50 kilometer grid. So we look at that NOAA study, give us some ideas, but we take it with a grain of salt, understanding that we got to look at localized phenomena a lot carefully before we could actually.
Right. Well, I mean, something to pay attention to is that NOAA study is historical data. It doesn't have anything to do with GCM. It's just rainfall recorded over 1958 to 2008.
Oh, that's just past history.
Right. And then in terms of the GCM stuff, that's a big field, and they're doing really good stuff actually at South Florida to do the downscaling. that you're talking about. You know, if you have a GCM, most GCMs have about a 3-degree latitude, longitude grid cell size. So 2 of them cover Florida, you know, that kind of thing. And so the projections that you get out of those GCMs are highly biased. And you can't really say, okay, this is how rainfall is going to change in Florida, you know, on a absolute level. But you can pay attention to the trends in the GCMs. And so, you know, the algorithm that we have does that. It basically applies those trends to historical rainfall patterns. Even doing that, I mean, if you talk to Obi at South Florida, he'll say that's not a good model either. You actually need a mechanistic model of rainfall in South Florida to really understand the physics of rainfall and how it's changing. So yeah, I agree, absolutely. There's a lot of uncertainty in that data. And you know, what we've taken is essentially the trends that the GCMs are projecting and just use those. And in fact, we're actually using 12 different GCMs, which are all saying different things about those trends and producing an ensemble to get best case, worst case scenario.
We're running a little bit behind, if you can hold your questions, get with Steve or get with Jack in the back, we'll move to our next talk. So thanks very much. So the next talk that we have is from our work last in May. We did a program, or doing a program called the Coastal Resilience Collaborative. That is a collection of people from all over the world that are working on coastal things. Atkins was one of the sponsors of the original sponsors of the collaborative. We met in the city of Delft in the Netherlands with a team of people, and I think we had 8 nations there or something like that. Even Turkey was involved, Ecuador, England, Netherlands, and I met Joost. And Joost is works for Delftland Water Authority. It has several names in the English, but but Delftland was formed 700 years ago. There are 23 water boards, water authorities in the Netherlands. I think it's 23 now.
It's 23, perhaps
Yeah.
22 very soon.
They keep wanting to consolidate them. The oldest one, I think, is one called Rhineland.
Well,
They
they're
claim-
fighting over that.
Yeah, they're fighting over which one's the oldest, and it was, they say 1260 was when it was formed. But it's the oldest form of, the water boards are the oldest form of democracy in the world. And they still run the same way they were formed in the 1200s. Elected people elect their representatives, and then they have a staff, very similar to our water management districts in Florida, in some ways. But Joost runs a thing called the Digital Delta program. Digital Delta is basically kind of the big data side of water in the Netherlands. And we wanted to bring in an international perspective, so I asked Joost to come and talk about the Digital Delta project. And I think you'll find it's really fascinating.
Thank you, Stan. Never been introduced like this. Let me first of all thank you, Stan and Florida Earth Foundation, to invite me over here, because I'm very happy to be here. Because as you understand, the data is very much comparable to water. It does not know any borders. So if we can't cooperate on this, where can we cooperate? I'm going to try to tell you something about this project called Digital Delta. And therefore I'm going to show you a short movie. But first of all, I really would like to thank Jay Martin, speaker of yesterday, to give me some information and some images that I will show you later on. I would also like to thank Henk Loesner from NEO to introduce the very difficult aspects and methods of this kind of big data. And of course, Steve, I want to thank you to give this introduction before I'm up here, because I found it very difficult to explain to people. That's why we made several movies to explain what Digital Delta is all about. And it will give you the impression that around the topic of big data, we all say and think, big data, that's going to be great, let's do it. And I will tell you today that we're going to do it, but we have to do it together. And second of all, we have to grow into it. And before I will give you some hands on how we think on doing that. Okay, let's start with a short movie on this topic. Oh, that's nice. It's always when you do this like this. Sorry for that. Is when you speak about IT doesn't work. Where are you? Is there any? Is that working? I hope this works in this way.
The Netherlands is a country with a lot of water everywhere, so being able to control and manage that water is very important. It's even more important given the noticeable changes to the climate, the growing population, and the increasing pressure being placed on infrastructure. Every day, individuals and organizations.
Okay, so much for the movies then. Let's continue.
Work with water with the recreational sector.
Yeah, I thought it. Okay. So I have to tell it to you myself, and I hope I succeed to do this. There we go. I found it. Okay, next slide. So what is it? It's a Dutch program that we are implementing together with a lot of parties in the Netherlands, mostly in the Netherlands, with a focus on worldwide. And it's being developed because of the fact that we saw that everybody in the Netherlands is working with IT and data, as are you all here, and we are all developing our own things with mostly of the time point-to-point solutions, which means that there is a data source somewhere. We do not know exactly where, but if we ordered it, we do know where, and then somebody will make for us a solution in its own language, with its own data, with its own systems. And if I want to use another data source, I have to pay extra money to do so. So we wanted to do it a little more easier, because we all know that if we're going to look at the future, we will see that water management in the Netherlands and worldwide will become much more expensive than it is right now. So we see a lot of optimization and cost effectiveness coming out of big data. That's why we started this, and I will tell you in this presentation how this will actually work. First of all, we think that now at this time there's a sense of urgency to do so. In the Netherlands, we now face €7 billion investments every year on water management. And we think that by the year of 2020 and 25, it will rise to 8 billion, which is quite a lot. So we need to improvise, and we need to find something that's bigger. So if we use digital data, we can actually, we think, grow into big data, and we think we can be more effective and more cost effective. So what do we try to do? We will try to arrange a solution that will help all sorts of users in the water sector. So we look not only at the governments to make better decisions to reuse data sources, applications, and also solutions for water management, but we also try to create a better way of going for working with interoperability with public and private products and information. We also look at science and knowledge institutes and how can they operate better in using such a world of free-flowing water data. And then more important, there's no innovation without our enterprises. Small, medium, large enterprises need to be able to use data in the future. Not only now, but also in the future. So it will help them to get a shorter time to market, and give them direct access to data. Well, it will also create a level playing field for data. And I'll tell you why that is important, because we found out, and you too, I learned yesterday, happily it's not only in the Netherlands, that there are lots and lots and lots of data sources, and even more than lots and lots and lots of data sources. The fact is we don't know exactly where they are. And if we know where some of them are, we do not know what they do, what language do they speak, so what kind of standards do they use, who are the owner, how do they get access to it. So we need to be able to do a better thing. And why is that? Because between 40 and 60% of the total project budget of most of the water projects at this moment is being used at getting access to data, searching for data, and then create new technology to use that data to be effective in a project. So we can do better, and we can use all the three parties to do so. So we started with this idea. And then they say, what are we actually able to do at this moment? Well, for example, as you can see here, or should see here, this is the area of Delft, which is here, as you can see over here, is the harbor of Rotterdam, Rotterdam Harbor, and the opposite side over there is the Hague capital, the political capital of the Netherlands. And in between there, we are responsible for water management, and we have some sort of a problem. And this problem is, we could call it blue-green algae, for example. There's a lot of blue-green algae in there. So at this time, we are using our pumping machines to pumping for water, to pump the water out, and just hope that all of the stuff that causes, I can't find the word in English, sorry for that, that causes blue-green algae to flush it out. And how do you do that? Well, we do it like this. We can do a better thing. We want to be able to actually measure what we're doing. But the fact is, if you look at it this way, this is, I think we can do it right now. It's contemporary, it does not in any way is comparable to what big data will actually help us to do. So we started another project. Another project is about salination. And that's what we did. It's the same area. And in this area we use all sorts of databases. Not only our databases, but also the databases of our national government, the city of Rotterdam, of the media labs, and private companies. And we aggregated that to see in what way we were able to keep the salt water out that comes into the sea, to this big waterway. And over here, this blue arrow, we have a big lock. And at that lock, sometime today, lots of big ships come into there, will give their products, will bring their products to the cities. And with that, a lot of salt water has come into this area and will also come into the area of the water world. We said, also, we need to cope with that in a better way. So if we combine the last project, and this is the last project that I've shown you, we combine all these data sources, we will actually be able not only to be reactive, but also to be proactive. So if there is salt water entering the system, we could see where it is, and we can actually act on it very effectively without using too much fresh water to push all the salt water out. That's the first thing, so we can react on the situation. But also, which is more better, in a very near future, we are able to look at the situation in Germany, which is all of the river, somewhere over there. And if it starts to rain over there, especially in a very dry season, we need fresh water. And at this time, our water is coming from the north side. We push it out in this way. But if we know that if it has been raining in Germany, we already know that there's flush of sweet water coming, and we can actually turn the flow of water around. So we can use fresh water to replenish our own water, which has been salted because of the drought. Is everybody still here? Okay. So that is also a small step to big data. It would be nice to do, but we found out it's not very easy to combine all that data. We have to do a lot of things, technically, but also socially, to be able to use all that data. Not all parties say, hey, you can use it, sure. We have to go back and convince them that we will not share it with somebody else. And other people say, yeah, you have to pay for it. We say, no problem, we'll pay for it. So we can do that now, and well, that will help us. But if you look at the future, we can do more. We can do a thing like this. And this is a very typical Dutch situation, but perhaps you have it here also. This is what we call a swimming water location. In the Netherlands, we have arranged it that because we like our citizens so much, we say if you want to go swimming, we arrange for you that there are pools where you can swim. The children can swim very safe over here. You can swim over there, and there's grass, and here, somewhere over here, you can buy something to eat. So when it's warm, at the same time, what you see, when it's warm, for several days, 30 degrees or something, the water is becoming warm enough. And then blue-green algae, Jay, they start to pop up. So what does the province do then? Because we cooperate with the province in that. They say, we'll plant this sign over there. And this sign says, careful, don't swim. Dangerous. So perhaps one of you in this audience, very smart audience, can tell me who asked the question for what that is the answer. Nobody did. Nobody asked the question, where can I not swim? What they want to know is, where can I swim? And at the same time, there are a lot of people swimming somewhere else, which is not being appointed swimming location. They're swimming there and they can do it safe. Nobody's getting sick. Perhaps there's a boat too much over there, so we can regulate it. We also know if you can do that several years. We also know that perhaps we should not invest in this sort of areas, because blue-green algae will come back all the time. We take another area where we know we can swim. We also know what kind of infrastructure is there. We also know what the probabilities are for more economical value over there, perhaps a supermarket or something else, or a parking lot with a supermarket. So that would be most interesting if you can do that. But if you want to do that, we need to be able to use more sorts of data. And it's not our data, it's data from somebody else. It's data, for example, from another mother that says on Facebook, well, if you're here, I'm over here, I'm swimming, look here, picture. My children are swimming over there. So, and also there are lots and lots of other organizations that have sensory everywhere else. So what would be the fact if we can use all of that information? That would be far much closer to big data, as I think it will be. But it's also very functional, and it will help us very fast.
Well,
if it will help us, it will also help Jay. I hope. And then, if it will help Jay, it will also help these children somewhere. Because of the fact that we said what we want to do with big data is want to make it interoperable. We want to be sure that if we find a solution to something using data and knowing what kind of solution is actually effective, we must be able to assess very quickly if the solution on one place will actually be effective on another place. So Jay is being helped. These children can actually swim. I've never seen a situation like this. So, and then you come to the most important question of all times. What will happen to our organizations, public organizations, if this happens? That's all bad. What will happen if somebody knocks on our doors and asks us, hey, you, what a board? What are the management authority? What kind of name would you like to use? You're doing the wrong work. I know you are, because I'm using data. All sorts of data here. I proved it. You can see it? You're doing the wrong thing. If you start doing something else, and I can prove it too, you'll be more effective. So what will the first reaction be then? Well, the first reaction will be, I think, a typical, well, I think it's Dutch, but perhaps it's also here, a typical bureaucratic reaction. Oh, so you don't agree with our policy? Okay, we have a process for that. You can go there, complain in threefold, and we'll get back to you in 8 months. That's the first reaction. Second reaction will be, sure, we're thinking of you, but we all have our own model. And I can prove in our model that we have the right model. That's the second reaction. This is also becoming a little bit more close to the next generation of well, what are management. But the generation on that, following that, will say, thank you, sir. Thank you for saying that. Perhaps now, I'm able to do my work more efficiently. And that's a strange thing, because if you look back at the last slide, you will find that big data will not only change the way we look at information, but it will also have a high effect on roles, role playing, and effect on who actually will do what. So there's a fisherman in the same water over there, and he's fishing, and he's actually being lucky. And there's a fish coming out of there. And we know so much about that fish, because our biologists are very smart. And we put it into big data, sorts of instruments, databases. And because of the fact that this man says, I found a fish, I catch a fish here, it's this fish. And we know that it hasn't been raining for several days. And we can find an app, Steve, an app where we can see how far the water is transparent. We can say very easily, hopefully, that it's safe there to swim. So at that time, you might ask yourself, what is the role then for a laboratory? How fast does somebody need an answer to a question if you look at water? So it's just one explanation or one example to do it. But the most important thing is, if we want to grow into it, we should be like ants. We should be like ants. We should keep wondering. We should be able to combine all the data. Who knows the data comes? And be able to see what will bring it to that. Because of the fact we don't know what it will bring us. At this time, we can only imagine things that we are able to imagine. But if we're going to aggregate data, there will be solutions we have never thought of before. So Alice will not be in one of them. Alice will be in water, data, lab. And we all work. So digital delta, that's a nice story. How does it work in practice? Well, we started by designing these principles. First of all, people said, if you want to do it, you must prove that it will work. So we started 6 use cases in 1 year of research. For example, Delta, Delft University, and about 6 to 8 national water management organizations, private companies, and showed that it actually will bring benefits to the organization. The desalination project use case I just showed you actually it will bring the Rotterdam Harbor a business case for about 800 million euros a year, only by doing it this way. But you must be able to facilitate reuse. Reuse is a very important subject. So I'll come back to that because of the fact we are burning money every day by implementing new solutions when it's not necessary. And also very important is data has to stay with its owner. Why is that? Well, just because of the fact we're not ready. And we will have the facts, I'm not sure if we ever will be ready. We will be ready to share all sorts of data with everybody, no questions asked. That's the first thing. And second of all is, are we able to contain all that technically all the data? So, then the fourth, it should be the first, the agile approach. The user must be central. So we all ask our users in the Netherlands, and we incorporated about 28 big users, also international users, and we asked them, how will digital delta will enable you to do your work more efficiently? And we got answers to that. And one of the answers we got is the fact that they said, whatever comes out of it, there's a small part of it that must be publicly owned. I come back to that. So that's also said, there has to be a situation where there's no vendor lock-in and also no vendor lock-out. So the fact is, if I'm going to make choice for one big system integrator, all other system integrators will say, you make your choice, I'm not going to go with you. So what did we do? What did we do? Sorry, difficult words. We designed a sort of platform that is a platform connecting platform. So we are also enabled to do this number 7. All existing platforms are able to stay there where they are. People are able to use their investments as it's been designed. So, okay. How does it work when you look at it? Well, it's work like this. You have a standard platform. This is publicly owned. This team all the way around is publicly owned. And what we say is, in order to find people, to enable people to find what kind of data sources are actually available in water management, we create a sort of big telephone book, a registry, what kind of word you like to use. And in this telephone book, you will find all data sources together with the metadata. We also develop together with Deltaris, a new sort of crawler that will help you get your metadata out of your system into the registry, so people know what kind of data is actually available. Who is it from? What will it do? And how do I get access to it? But there's a problem there, because a lot of the data is being developed in all sorts of technical standards. And we found out there are more than 200 standards in the water domain. So we want to say, if you want to aggregate it, go to big data. It's much. It's almost impossible to do. So people say, we must go back to one. Use one standard. Well, That's the one thing you never say that I found out. So we use the principle, and it's called the 1+ principle. So we said, if you want to go back in this area with the usage of standards, how should we do that then? Then we look at the total standard that has been used, and we see what percentage is most effective for the total sector. So we say, for example, we take 80% of the standard, and then you will see we have about 30 standards you can use in this platform instead of 200 something. And those standards are not only water boards, used by the water boards and used by the national government, but also international standards. They're standards used anywhere on the world, open standards, or standards that people say we want to use. They're not open, but if everybody says we want to use it, it doesn't matter. What we want is interoperability. So we didn't do that. So if you want to use a thing like this, which has a central point where you can access, not only as a user, for example, as a government to discover new solutions, or as a private company to create new solutions, when you have access to all this sort of data that's in here, or researchers that can accelerate because then at one time they will have access to all that data. Then you have to be sure that all things that are going in there must speak the right languages. So that's one of the things I'm going to tell you next slide, I believe. And it's the fact that we have to grow into that. We have to grow into maturity, because big data is actually a small child. We will grow into that, but we need each other to do something. So what can we do with this platform over here? We have users, and you have project developments. And this is actually very important why we have those. Because, as it says over there, this system will work and it will grow by the fact that people actually use it. And how can you use it? Well, you can use it simply by saying, for example, in the US, we have the same system as you have in the Netherlands. I'm going to use it, and I'm going to use one of the projects I'm actually planning to use. So I don't need any more new money. And in that project, there is money to use data, to use IT. And if you use that to get connected to this platform, the next time you do not have to pay for the connections anymore because it's already there. And the next time that you go there, there's somebody else that used it, and you have, without extra cost, access to data from somebody else that you actually can find. And you also have access to other persons' applications. So if you have an application here in the north of the south of Florida, and you use it there, I actually am able in the Netherlands to reuse it. It's also good for your enterprise and companies in the other way around. So it looks a little bit like a sort of app store. Only this is an app store, it's a strange app store, because the fact that people are afraid of, I don't know if it's good or bad, but people are afraid to use each other's commercial solutions or platform. We have a publicly owned base, small layer. And above it, you will have an ecosystem. That ecosystem will develop itself. That's the promise of digital Delta. Okay. So I told you a bit of how it will grow by using and reusing projects and information and data. Because once connected, always connected. But it doesn't mean we do not ask questions to each other. For example, if you want to join, we ask you to give all of your data sources and enter it into this telephone book. And then we say, okay, are we able to do something then? Well, at this time, we're not able to be interoperable. We're absolutely not. We have to grow into that. We need some sort of harmonization. And we need a point on the horizon that we want to grow to. We must allow ourselves to go there. So we have seen several presentations in situations where you can actually do that. So how will we be able to do so? Well, we have to see in this paradigm, I don't know the English word for that, so for that. We have to start behaving differently. First of all, we have to start reusing what's already there. We do not have to discuss all the year about if data is actually open or not. You just start with it and actually make small progress in there, but make progress. To share data and data harmonization. So data harmonization is already been talked a lot of times in these 2 days, but it's a very important subject, and also because it's still being organized into silos. That's very true. But we will go out of these silos. The more fishermen we have, fish we have, and all sorts of data sources we never thought of, the less silos we need. So we also need perfect data. We think now we will go to a situation that we will agree to each other. This data is usable. So therefore, we must also say to each other, okay, we will use, for example, the same framework in order to say this is quality, that's the sort of quality data, and that is not. So everybody is using different things. We will have to use and start to make agreements with each other on how to do that. So there are several steps that we looked at already for a long time. There's several steps. We like to see that these steps will actually help us growing into them. And if you look at the maturity model, you will see that we don't make any, we don't have any ideas that it will happen in the short term. Now we think, if you look at the short term, data must be available, findable, accessible, and insightful. And also, in the mid-long term, data must be usable, to be harmonized. So also the segmentable part must be arranged. If somebody says this is a sewer pipe, another one says this is a poop pipe, do we actually mean the same thing? In the long term, we want to go to reliable data, centralized, reusable, and of course, in the end, at the horizon, which might be in 2 years, it might also be in 20 years. We want to be able to use big data for analysis. So big data is more than just a lot of data. It's all sorts of data. It's all sorts of data that you could choose from in order to be more effective and more to the point where we good water management. So I'm going to skip this thing, but this is something that we found useful to look at. If you look at the different stages, findable, harmonizable, useful, and reuse is Dutch word for reuse, and betrouwbaar is developable.
Thank you.
You'll see that it's actually not a very difficult thing to do, but we have to take care of the fact how we talk to each other. We have to have enough patience. So, where do we go from here? In the Netherlands, we said we're going to use it in the biggest programs there are. Most of the governments are active on So we're going to do that. And then, in order for all people to understand what it will be, because it's difficult, we will send people to help them in the phase that the project is started. So there is not a big issue on semantics, because that's on every corner. And communicate, as I'm doing it right now. Communicate, communicate, communicate. Frappe, frappe, frappe to you, as the French say. Use existing systems as solution. I already told you something about it, I will come back to that. And then, most importantly, connect. Don't be afraid to connect with each other. Don't think that it will cost lots and lots of money, because you're already doing it. And if there is one government organization that is able to pay for small public labor, and you have the guts to go with it and spend your project money every small time to go with it, it will grow and it will help you. So, what can you do then? This. The judo principle. You already know it. I already told you about it. This is what we're looking at. We're already doing it. But the fact we have to do it together. If you can see, the world is linking, or it's calling. Don't know the word for that. But if you know that about 60% of the world population in 2050 will live in Delta, and these are only the highly urgent Delta areas that I'm showing you here. Because if these Delta areas have the same problem as you have, we need to work on it, we need to cooperate with that. Because it will also depend on economical, the way the economy is flourishing. So the institutes are big, and so the investment, not only in the Netherlands, also not in Florida, not only in Florida, but also in Bangladesh, and also in Mozambique, and also in Egypt and now Delta, as we call it, Indonesia, of course, Vietnam and the Mekong Delta, and they're all very much comparable. So, are we actually able to start with big data? And we say, yes, of course, you can do the things that I just told you, which are mostly keeping it to yourself, doing the things it's in your own scope of influence to do, connect with each other, and then start doing things that will actually help. So if you have a situation like this, you do not have to ask any search machine. Because if I ask a search machine in the Netherlands for a flooding solution, the search machine is the most friendly, user-friendly machine there is. It will give me a result in 0.27 seconds. The number of 127,000. Ladies and gentlemen, it's even worse. If you look at it, for example, in Asia, if you have a situation like that, you see the face of that man, what's happening over here. 50,300,000 results will give me a solution. But people say, yeah, it depends on the things that you will put into as a search machine. Yeah, sure. But if I have a situation like this, I really would like to know, is there a solution for me? Will it work? Will it work? So how do I know if it works? Well, most important is, if I go on the internet and I go to the first 100 of them, I will find a company that will always say, yes, this solution will work. But what I need is a reference from a trusted government or a trusted organization that will help us, tell us if the solution actually works. If we use that solution, reuse that solution, we're able every time a little step further to see if a solution will actually work in our situation. What kind of delta, what kind of area in the world? If if it's in waterboard, one of the waterboards in the Netherlands, or in the big deltas, that will help us. So, of course, this doesn't work either. I had a workshop show that. We have developed a tool for this, and it's called water window. A water window is aimed at the reuse of water solutions. So what we're doing here is this website. Go there. We just started it. We're looking at solutions that are implemented anywhere in the world. We started in the Netherlands, of course. You have to start somewhere. And we look at the fact that at this time you cannot find a solution for your problem without knowing what the solution is. Water window will give you that solution, but it will give you more than that solution. It will also answer the question if a solution to this is a problem, this solution, is actually being proven or innovative. And proven means that only a government in the Netherlands, trusted organization, can give a reference about a solution and will tell you, yes, I will use this solution in a primary process on a structural basis, and I will actually say to other people, you can use it. So only the proven solutions can be publicized by governments. Anybody else can publicize innovative solutions, because we want to know what kind of solutions are there. So if there's another proven solution for you, you will know that there's something in development. You also know it's not proven yet, and you can see what kind of development stage it is. So you will be able to call those people and say, well, maybe you can help me. So if this database doesn't give you an answer on, is there a solution for me? It's proven, and if there's not, and if it's not, is there a solution for me in development? Then you can go to the water agenda out there, and you can post your question to all sorts of companies and knowledge institutes, and you say, I have this problem. Can you help me fix this problem? By using data, it will not take very much of your time to create it, because you already clicked into this. So you know what kind of characteristics you need to solve your problem. You only need to add on that. So if we're able to do that, you might ask the question, is digital delta then the holy grail? No, it's not. No, it's not. The fact is, we would really like to see that the fact that digital delta is seen by all its users as a publicly owned layer. That perhaps that word public doesn't say Dutch. It doesn't say also, you can do it in every country. Use the same principles, and then see if you can be interoperable with each other. Have your own ecosystem in your own country. Be able to use big data within your own country. And on the back side of it, be able to do it between countries, worldwide. That would be some point that put on the horizon. So, then I come to the fact of the angels, big data. You ask yourself, what is that all about, the angels? I'll tell you something about through a story. And the story is about two men that walking around the street in Italy in about 1505 or something, that year, a long time ago. Two men, and one of the men is an artist, very well-known artist,
Michelangelo?
Yes, sure. What did you say?
Michelangelo.
Michelangelo. He's walking off the street with his friend, and at one time, there's a big brick in the street. And they're walking there, and his friend says, hey, what's a brick doing here? And he tries to kick it away. And Michelangelo says, don't do that. Why are you doing that? Why are you kicking this stone away? This is a beautiful stone. You shouldn't do that. And his friend says, well, it's just a stone. Kick it away. Why? It's just a stone. So Michelangelo, he picks a stone, takes it away. And he said, okay, I'll take it. See you next week. And 1 week later, his friends come to the atelier, to the working space, Michelangelo. And what he sees there is mind-blowing. Oh, sorry for that. He sees this beautiful angel. And he goes, wow, this is beautiful. What is it? I said, I made it. I made it just for you. Because of friendship. And friendship is that important. I made this statue just for you. And you know the more important part of it, I made it from the stone that you kicked away. And he said, oh, thank you. It means a lot. So then, ladies and gentlemen, why do I tell you this story? I can tell you, the digital delta is that stone. Thank you very much.
Okay, we've got time for maybe 1 or 2 questions, but I think that, what's that?
No, sorry.
But you can see that they are doing some incredible work there. I love the Michelangelo story of what you can create out of something that is somebody else's trash is somebody else's treasure, or it can become that. So, question.
No question.
No question.
It's the first time in my life I've been clear.
But get on Digital Delta. The industry partner for Digital Delta is IBM, and they have a whole suite of folks in the Netherlands that worked on.
Yeah, perhaps I can elaborate on that. We had a first year of research in order to establish what is needed if we actually want to answer the question and what we need to be able to work with big data. So at that time, we worked closely with IBM and we used software of IBM. But one of the findings also of this stage was no login and no logout. So if you want to be successful, we have to decide upon a platform that people actually want to use. So since IBM has several platforms of its own, at this time IBM is involved as just another user. But we also keep it involved very much because it's very highly regarded knowledge partner that we have. But at this time, only public entities are developing digital data.
Okay. Any questions? Yes.
Is there a report or some publication?
Yes, it's about printed. Yeah.
As soon as that comes out, we'll make it available.
Yeah.
So much of what we're talking about is incorporating data from different sources. I mean, does the European Union know about all this stuff, and what's their take on it?
The European Union know about all this. It's a difficult question. The European Union is it's not a monster, but it's an organization with lots of heads, and it tries to stimulate all sorts of innovation. So I know there are several developments that actually cope with the aspect of big data. But the way we use it is quite unique. So we have a board of stakeholders. One of the agents in there is the European Commission. We have 2 sides. Yes, they're developing other things that are actually looking at the same topic, not on water, but also on big data. But on water, the European Commission is actually one of our stakeholders.
There is an app system that is being developed by 6 nations in the European Union. It's the head development is at UNESCO IHE, which is our university partner that we operate our Netherlands programs out of. And this app they're developing is one of the most fascinating apps I've ever seen. What it does is that you stand in a location, you push the app, and as the water comes up over your ankles, it will tell you where the next highest building is to get out of a flood. So you might think, oh, that's no big deal. Well, yeah, it is, because of the fact that what if that building is full of people and has no capacity to get you in it? So it will pick for you the next building that's available so that you can get out of the flood and directions to it. So it's an application of big data that, I can't remember the name of that.
I can't either, but it's just another step to becoming big data.
Yeah. How do you use big data to actually save people's lives? Is what that one is for. And I think that it could be very useful. And we talked when I was talking with people that are developing it in May. It can be very useful. For example, what could you do with that in San Francisco?
So as I look at this is just another application.
Yeah.
If you have a platform where people, enterprises can access all this kind of information, they will develop that sort of things for you. Try to get it on the market.
Yeah. Okay, let's take a break, and we definitely want to do the full 15 minutes, and we'll try to make up time later on.
Has he been working from home mostly? Yeah, it's kind of crazy.